You should know I'm a mathematician, but you should know I come from finance. So I'm going to start the way I like to start many of my talks. I want to play a game. Actually, I want to play two games with you. In the first game, I'm going to give you a choice. Some of you know this. Okay, that's okay. Still play along. Okay. In choice A, you're going to earn $900. And in choice B, you don't know. You could earn $1,000 with a 90% chance, or nothing with a 10% chance. Let me do a very quick show of hands. Who goes for choice A? That's very typical. Who goes for choice B? That's very typical too. It's about 10% of the people. All right. Let me play a different game now. With a 100% chance, you're going to lose $900. Or you have a different choice. With a 90% chance, you can lose a little bit more, $1,000. 10% chance, you lose nothing. Let me have a show of hands. Who goes for choice A? That's very typical. No, okay, so who goes for choice B? Okay, so you just proved a few things. So you proved why sustainability is going to be so hard to achieve. You just proved that climate risk is a real risk. By the way, you also proved why Trump got elected. Yes, yeah. But that's a different talk. I'm the director of the program in mathematical finance at the University of Toronto. And for a number of circumstances, I switched into sustainability in the middle of the pandemic. And the reason was I got called to help the government of Ontario with the financial considerations of the intervention measures that came out of the pandemic. And I found a new world that fascinated me, including public policy. Okay, that was fantastic. You should also know that Ivy is a graduate from my program. And she did something very remarkable, which is that she was managing the risk for the bond portfolio of the province of Ontario, which must be a very difficult job. She left that job to join me to do this. Round of applause, okay? That's the perspective I'm going to use today. It's a mathematician talking to you, but it's a mathematician with a financial background. I've managed, I was the CEO of my first spin-off from U of T was a company that I created in 1999. And it was a asset management company. We invested money, about $1 billion for 25 years. So I know about money flows. And I wanted to use that to understand sustainability and to see what we can do with that. So this is a version of the same game, which is, imagine that you're in this situation. You're at the airport, you're catching your flight, go home, and they say, well, there's a federal regulation. Airplanes cannot take off when there's a storm. Actually, the airport has to shut down if there's electric storm. But let's say that you're in a country where that doesn't happen, okay? Shall you fly? Will you risk your life to get on the plane? But that's the same game that we played earlier, right? Game 2, isn't it? So what made you change your mind? The same game. So
my life is worth more than $1,000.
There you go. So this is very important because at the end of the day, a lot of these things come down to numbers. And I'm going to be talking about numbers a little bit. So let's look into this. I call risk thinking. I'm going to explain a few things about risk today. And risk thinking is something that we need to learn how to do. Okay? The human brain is very interesting. There are two interesting parts of the human brain, the limbic brain and the frontal neocortex. The limbic brain is a fantastic risk management machine. That's where we're alive. The frontal neocortex is terrible. And that's the one that we use when we're making certain decisions, but the limbic brain is the one we use for make other decisions. Okay? So let's get into that a little bit. Arguments in favor. Probability. Probability says it's very unlikely anything is going to happen. So why would you lose the price of your ticket and not jump on the plane? Furthermore, physics, Faraday law would say that if there is a storm, just going to go around the plane and no problem, you're going to be safe, right? Okay, arguments against. If you're going to do that, this is very compelling. It's very, very compelling. As you said, it's very compelling. So how come that when we talk about sustainability, we think of it as game 2 in the previous slide and not as this one? What is there to make us do things differently? So let me tell you a little bit about risk thinking and why a mathematician is here today. When you're doing risk thinking, you need to organize your information in 3 different buckets. The first thing is what we know, the known knowns. And by the way, I loved yesterday. It was great. I've learned so many new words. I loved it. And a lot of what I heard is known knowns, which is great. And a lot of science is based on known knowns. But known unknowns is where I live. That's what I deal with. And some of you deal with that too, but not many people deal with that. And that's where we don't have enough training, right? What do we teach our students? The known knowns. Who teaches you about the known unknowns? Life does. Well, that's the mathematics I do. That's the mathematics Ivy does. And that's where we spend our time. By the way, the really concerning part is the unknown unknowns. And the whole process, the whole quest of learning is to try to move things from the right to the left as much as possible, right? So let's put this to practice. Climate risk in 2024. Known knowns. We know, lab experiment, that the sun radiation warms up CO2. It's a molecule that spins very quickly, and that, because of thermodynamics, makes it hot. We know that. And we know that methane spins even faster. And nitrous oxide also. By the way, water too. But we don't care for water. Why? Because it rains. That's the difference between water. So all of these are things that we know, right? And you put them together and now you're concerned. And this is the problem. The problem is that when you deal with the concerns are really known unknowns, because we don't really know. For every argument in favor, there's an argument against, right? We haven't experienced that. And imagine someone trying to convince you to jump onto that airplane. Said, we really don't know if this is going to crash, right? We really don't know. And it's true, you don't know. But you made a decision. That uncertainty is just too expensive. Okay? So the known unknowns, which is some of the facts which are being debated wrongly, is the temperature of the atmosphere will probably go up. Why? Because we have the lab experiment. So the known knowns tells us that the temperature of the atmosphere will probably go up. Now, there's a chance that it doesn't. There's a chance that there's something that makes the air do something that and then it doesn't. There's a probability of that. The experimentalists that work on this and they do the models, what they would find is that most of the time it will warm up, but there is scenarios under which it doesn't. And this is what people hold on to say, well, maybe it doesn't do it. And then they play game 2 the wrong way. That's what's happening. Also, we know it could cause volatility, wind, rainfall, etc. Polar caps may melt. All of these things are things that we project that they will happen, but there are arguments that would say, well, maybe they don't. And this goes back to the game theory of the beginning of the talk, and that makes people make their own decisions. And of course, the unknown unknowns, we don't know what they are. So we have to work with the known unknowns. And when you deal with this, I have to give you a brief history of finance, because finance is going to hold a key to understanding some of this. I'd like to talk about Hammurabi. 4,000 years ago, he invented the insurance sector. Now, I'm going to start today. I need to tell you all of this. We need the 4,000 years of history in 2 minutes, because where I want to end up today is Article 210 of the Paris Accord, which says, and this is very important, it says finance flows will be used as a pathway to low greenhouse emissions. Article 210 of the Paris Accord says that we're going to use money to capture carbon. And 193 nations says, yes, let's do it. By the way, COP29 started 2 days ago. And on the first day, they already approved one of the articles in the Paris Accord to be extended, Article 6, that this is about finance. Well, this is accepted. I'll tell you a lot about this today, but just 2 days ago, they approved that they're going to permit countries to trade with each other emissions. That's very good. Okay, that's very, very good. Now, but if I tell you what happened in the middle, a few things which are interesting. This is just fun. Thales, the mathematician, he saw that there was a very big olive harvest, so he bought the right to use the mill 1 day in the year. And of course, people didn't know about option trading, but he didn't either. He just invented it and made money when all the olives went into the mill after the harvest. Very, very interesting. Okay, now this is more interesting. The first known exchange was built in Japan, in Osaka, in 1697, and that was for rice. This is very, very good because it permitted buyers and sellers to agree on the price for rice in the future. It eliminates uncertainty, and it's been with us for a long, long time. Of course, after that came Chicago, which was really the city to incarnate the concept of exchange, agricultural exchanges, much to the demise of Winnipeg and Minneapolis and the other cities that were just markets. Chicago became the paper market. That was far, far more interesting, right? So that was there. But to understand what I want to tell you today about where we stand and how financial markets are going to be relevant for sustainability, I need to make another reflection. You would probably disagree with me. Doesn't matter, we're here for that. Okay? But I have a way of thinking about the 20th century, which for me is a century. What's the best thing that describes the 20th century? I think this is the man on the moon. First, there were no women, okay? And second, it's something that was done with very little data, something that was done with lots of equations, and it happened in physical space. For me, that's the science of the 20th century. The 21st is very different. And again, I told you, you would disagree with me, okay? I can see some people say, no, I completely disagree with that. That's okay, we can debate that, okay? The 21st century is going to be different because from my perspective, it's going to have lots of data. By the way, equations are gone. I'm a mathematician. Many of my colleagues disagree with me on this. I don't care. Okay? I think we have no equations, and everything happens in mental space. The 5 largest companies in the world, 4 of them, nothing physical. That says something, right? The value of the mental space is enormous, and that space to be conquered. That's, by the way, that's where I like to live. So if you accept this, then we have a way of thinking about sustainability. This was Kyoto 1997. Kyoto 1997 was, in my opinion, something similar to Osaka in 1697, because what Kyoto 1997 said is we're going to create a massive market for CO2, for emissions. By the way, there's also markets for methane and other things, but CO2 is the big one. And this is a market where people that capture carbon can trade with people that emit carbon. So I want to tell you about the things that we do. And I like to choose the 4 Aristotelian elements. I start with Earth. Okay, this is something what we're doing. And it's completely within the context of carbon trading. This is a tool that we've built. And it does the following. You select a location where you're going to do a forestal project, for example, and you select the type of tree you're going to plant there. Then it's going to give you the outputs over time and the monetary value of that investment. These projects that will capture carbon, you know how much money they require to launch, to invest. Back to game one of my first slide. But you don't know what they're going to give you. And the thing is, with forestal projects, the growth, the biomass growth, is to the inch. You can predict it. It's very, very well known. Of course, we have a lot of unknowns, a lot of variables. Climate change will change the output, but we have a pretty good way of coming up with the cash flows that a forestal project will give you. And this translates into dollars, which is what investors need to know. The price, you know, the price of a ton of CO2 is about, depends on where you buy or sell it. This is a market. It ranges between $10 and $50 a ton. So if I capture carbon at a certain rate, then I collect money, and it's about $1 a year per tree. Right? But we can calculate that well, and then you can decide if that investment is worth it. Okay. By the way, there's a very interesting application of this, which is no one really knows the price of carbon. From this perspective, this is good. This tool will allow developers to develop projects. Let me talk about water. This is very interesting. Something happened in Kenya. We were not involved in this, okay? I'm just a consumer of this. A company, Vestergaard, created a project to bring 880,000 filters for water. This removes from the atmosphere a lot of, I'll tell you exactly how much CO2. And the reason is that in Kenya, if you want to have drinking water, you have to do that. And now you can do that. Do you know how much this is? 2.7 million tons of CO2. Look at this, $27 million for 800,000 filters. It's very interesting. So this is what math means to me. But here, now I need to quote a very famous mathematician, Paul Erdős. I don't know if you know of this guy, but he says something very interesting, which I like to tell all my students. Said, a mathematician is not someone who knows how to add. It happens to be a mathematician, and they say, oh, well, here's the restaurant bill. You divide it by 4. It happens, you know, maybe you do that to your mathematician friends. No, he says, no. A mathematician is not someone who knows how to add. It's a mathematician is someone who knows why and when to add. And I have a very good example of that coming up, which is another thing that we have done. All of this is done by my research team, and Ivy is one of the leaders of that. Look at this number. This is a table, very frequently quoted. This is the emissions by country. Okay, you probably have seen that. Just 2 days ago, as I was reading the news about COP29, again, they're talking about the big country emitters, China, United States, India, right? What's wrong with this table? Well, China will very quickly point out, say, well, this table is wrong because that's the total emissions, but it really should be divided by people, right? And when you divide by people, of course, China disappears. And then a very interesting country comes up, Canada, number 7. Actually, Canada is number 7 no matter how you look at it. But which of these two tables is right? Well, let me tell you, they're both wrong. Because that's not how you should count emissions. Dividing by population is also not the right thing to do. And not dividing by anything is also not the right thing to do. So this requires a little bit of thought. So let's go back to Paul Erdős and say, well, how do we look at these numbers? What do these numbers mean? So we took this challenge and said, how could I come up with a way to attach an emission number to a country based on what the peers do. So if you've done linear regression at some point in your life, right? Okay, well, linear regression doesn't work, but it's something like that, what we did. We wanted to understand emissions in socioeconomic terms because, well, we found that these are the features that matter. We use support vector regression for that. You don't need to, it's a tool in machine learning, not important. But it shows me where emissions come from. So for example, urban population or population, right? If you don't know these things and you want to reduce emissions, what would you do? Just kill people. That will reduce emissions for sure. Yes. Or just don't grow the economy, as some people may be suggesting. Well, that will reduce emissions for sure too, but these things are not in the works. Oh, by the way, you can give Quebec to France and then Canada will lower the emissions too. But it's there, but these are not the solutions we're looking for, right? So understanding the cause of things is very important, and mathematics does it for you. That's what we do. That's what we like to understand. And once we can do that, then we can do better things. And by the way, this is very important because in the targets that every country was assigned at the end of Paris, or the Paris Accord, we're approaching the time when they're going to realize that they cannot achieve them. So they're going to have to rethink about them, talk about them, and throw their weight around each other to make sure that each country can get a lot of emissions and reduce everybody else's. That's coming. So I'm getting ready for that to say, well, maybe I can do something about this, right? And that's what we're trying to do. And the result is quite interesting. Let me just show you. Again, this is just for us, okay? So what we did is something very, very, very simple. So since I can predict, or not predict, just how can I say, assign emissions to each country based on what everybody else does, based on the variables that matter, let me look at your actual emissions minus the emissions which are your fitted values. And this is what we get. Here are 16 countries. Okay? So that one is interesting. That means that their emissions are going up. Again, these are emissions not in absolute numbers. The absolute number is meaningless. Or also not per capita. Per capita is meaningless too. Okay? That country, whichever you want to know. I'm sure the UK disagrees with this picture. But that's okay. Write your paper. Write your paper, and I'll read it, and maybe I'm wrong. But that's my paper. That's my result. Okay? Then I have countries that are becoming greener. It's Australia. They're probably very happy with this. Then, okay, let's write the next paper together. Understand? This is something that can be done, and this can perhaps put every country onto the same level playing field, and then we can have reasonable emission targets for whichever next year we choose for these targets to happen, okay? And now I want to end with fire. That's the fourth Aristotelian element, which is actually the most interesting for me, because fire is typically associated. So it's for me, sorry, for this talk, okay? Because fire is associated with, forest burn, and then CO2 goes back into the atmosphere. But I want to show you a case. It's a business case of a tribe in Northwest Australia that is actually paid money to burn the savanna in a controlled way. Very interesting. And again, it's to carbon credits, back to the trading mechanism that I told you earlier. So that's where this Nyaliga tribe is in East Kimberley, Australia, right up there. And savanna fires, they happen naturally, okay? And the thing is that when they happen on their own, they typically occur at the worst possible time, when the land is very dry and they burn at scale and for a long time, and they have a lot of emissions. So then they gave him some money. We don't know how much. I have a thesis. I think it's about $1 million a year, but I don't know. Just based on the price of carbon, okay? It's about $1 million a year. For $1 million a year, what you can do is you can do controlled fires. so that you have the fires during the wet season and not during the dry season. And they said this, I don't know about that, I only know about the finance, but they say a way to do that. And just think that project will be, I'm guessing, about $1 million a year. Just that. Okay. And when they did that through this controlled burning, what they found is the area that burned was reduced by 33%. All of the grass and the wildlife are coming back. And drum roll, and this is what you get paid for. You don't get paid for this, but you get paid for this. The CO2 emissions are reduced by 40%. So you calculate the emissions and you get paid. But now, this is my final point in my talk. How do you calculate that? How do you calculate the reduction in emissions? So I'm going to try to explain to you how interesting this is. I'm going to try, okay? Because there is a lot of documentation which is used to do that. And here we have some of the documents which have to be produced to validate, to approve, and to eventually get paid for that. These documents is about this thick. They are done by humans and take months for them to be done. There's a lot of checking that has to happen. This is what consulting companies do. KPMG had a plan to hire 100,000 people to do documents like this. By the way, a carbon trade, do you know what the commission is for a carbon trade? 50%. It's the most profitable business there is right now. 50%. So much work. And not only that, the buyer doesn't know the seller. I have a lot of business ideas for that, but let me not talk about that, right? Because that's a lot of money. Who can tell me perhaps a faster and more efficient way of doing a carbon trade like this? Let's focus on the Nyaliga fire case. Well, you have to use large language models for this, of course, because large language models with very simple data sources like satellite data can make this work in minutes. And we need a lot of these trades if we want to remove a lot of CO2. So I believe that the reason that the removal of CO2 is so slow is because we don't have the mechanisms to make these projects that could remove them go faster. Whether it's hydrogen exploration, whether it's controlled fire burning, or whether it's planting trees in the right part of the world. Math in all of its forms, whether it's large language models, machine learning, or any of that, will be able to speed this up. I explain this to my students who, they come to my program, they want to be traders. Who wants to be a trader? They want to be traders. And I tell them, there's no money in trading anymore, right? And I try to explain them how you would buy and sell stock when stocks were created in the 17th century. It must have been very interesting, but see, must have been exactly like this. The 17th century version of this. Now you can buy and sell a stock in a minute, in a second. What am I talking about, right? Why? Because we have accounting systems which were developed 100 years ago. They're trusted. You lie on the accounting system, you go to jail, right? And this is the system we've built, but we don't have a system for that. But we have all the tools to build it. Okay, so I'll end with my wish. This is what I believe we should do. And yes, you have to put a mathematician in your life. Okay, thank you very much.